And cellular automata are a lot of fun because they're very simple string rewrite rules. People in computers like them because you study cellular automata and you keep finding ways that you can run a general purpose computer. So there's this guy in San Francisco, actually across the bay. He came up with a cellular automaton that, to my practiced nose, smelled like Kabbalah. And I've been working with it for a few years, and I think I have it sort of dialed in to where it's supposed to be. The original machine is called Knock, and he's written an entire operating system called Urbit that runs right now. And when we get to the future of the internet, we'll talk about Urbit a little bit. So
Knock spelled how?
N-O-C-K. Mine is axe, spelled like this. So any rewrite rule, you've got a left and a right, one or more steps between. I'm going to do this part as best I can. Hold on to your hats. So, imagine you were kidnapped by aliens, and they put you down in front of something that looks a lot like a VT100 terminal, and told you that there was a magic computer trapped inside of it that worked on numbers. Right? Your keyboard has letters too, but they gave you the numbers as a hint. And you kind of sense that they're watching, and it might be important to get stuff right. What would be the first thing you would type in?
Pardon me for a second, I have to go put money in here.
Sure. Anyone?
What would be the first thing that you would type in?
To the computer, yes.
As a letter?
Well, they did say numbers, but you've got the whole keyboard.
1.
You would type in 1.
0.
2.
She would type in 0.
I'm just trying to figure out which one you want. I'm gonna give you the thing.
I've been typing zeros, but that's just because I saw the face of the aliens. If they had more like shag or something, it might have been 1. But it's a 0.
There you go. That's
which is okay because it doesn't work. I mean, either way, it's not effective. We infinitely loop.
Doesn't really work.
It doesn't really work.
Anyways.
But we do know our 19th century set theory, so we're going to try something else. We're going to try I'm not going to keep doing this forever. Eventually brackets will just mean that we're asking something. Oops. Also a failure. So we've learned something, but we're stubborn and persistent, and we really think 0 is the correct answer. We're not going to try and fall back on 1. If we did, we would also fail, so it's good that we don't. Gives us 0, 0, 0.
Oh yeah.
Just a good old ordinary 0. And what's cool about that is we're no longer infinitely looping. See, ax 0 goes to ax 0, ax 0, 0 goes to ax 0, 0. Now, if you have a computer, you have something that can crash, because computers are capable of being in a state of error. So in this computer, if you're crashing, you're either looping or you're infinitely looping. So these are a couple of our crash defaults. This, on the other hand, is an operator, and we'll get into how it works in just 1 second. Speaking of 1. Can we produce 1 by continuing to chain zeros? Wouldn't that be tempting? 0, 0, 0, 0. 0, 0. Yeah, maybe on the West Coast you can make 1s pop out as zeros just by magic, but in a real computer you need a high bit, namely 0, and a low bit, namely a 1. So if we try 0, 1, 0, 0, we will very naturally, of course, produce 1.
1.
Yep. But how? I'll get there. I'll get there. Because we're going to try 0, 1, 0, 1.
You missed the whole God part.
Anyone?
The whole thing. 2.
Thank you very much. Gold star. Anyone?
2.
Wild ass guess? I heard a 3.
2.
I heard a 3.
Yeah, she's like, I heard 3. You got it.
All right.
It comes to life, yep.
So let's ease up. What did we just do?
Sounds score.
So what we just did was we used our first three operators. Operators always work on compound cells of, they're not actually cells of three. So now we're going to talk about our axioms a little bit. We have either an atom, which is any number, any natural number that's from 0 on up, or a cell. And a cell is an ordered pair of two nouns. We just defined a noun. So it's recursively defined. Sometimes I refer to a cell that contains two atoms as a pair, if it comes up, which it occasionally does when we get to stuff like llamas. So when I say this, it really means this. And that's actually important because there are two ways to do it. These brackets could have been over here. Do you see what I'm saying?
Right, yeah.
Yeah. So one of these, this is the operator. So the operator is what we call a catter if we're doing list, but it's at the head of the tail. And the operator 0 returns the argument without reference to the subject. So if you say foo 0, 23, you get 23, and so on. So 1 is our addition operator. So we got 0, 1, 0, 0. Which, what it does is it evaluates these two. Key thing. So it takes 0, 0, 0 and axes it to get 0, and then adds to it to get 1. 2, 1, 2, 1 is the fun part. This is the branch operator. 2, 1, 2, 1. So here's our operator. And what branch does is it selects from over here. And first evaluates it. So we got the 1, 2, 1. So right. Yeah. Brain fart. So we need to evaluate this part. So it goes 2, 2, 1. And this is the 2 operator on branch 1. So if this were a noun, and I'll do this part on another page, there would be more than one option, right? So you might have 2 or 3 over here as a pair, in which case 2 and 3 would respectively address it. In this case it's 1. So it returns 2, and then we add it, we get 3. So branch, the addresses are like so. So you got nouns that can look like this, and
What's the name of this kind of math?
this is a cellular automaton. This particular one's called AX. It's based on knock. The order of the operators and a couple of the operators I chose are original. So for something like this, you have the 2 operator can have 0 actually, in which case the return value is not defined, which becomes important later. Or it can have 1, and 1 would return this entire noun. Or it could be, say, 2. 2 would return here. 3 would return here. This is 4, 5, 6, 7. This is actually easier to see if you write it in binary, because you got 1, 10, 11, 1, oh, is that right? Yeah, I think so. No. Anybody want to help me count?
What is it? In binary?
Yeah. So I skipped one. Well, 1, 1, and then 1, 0, 0. Right, of course. 1, 0, 1. 1, 1, 0. 1, 1, 1.
Yes.
Speaking, writing, and thinking all at the same time can be a little taxing. But so this is how the branch operator works. You take and you select. Does anyone want to pause that thing and take a 5-minute break?
Sure.
Cool.